Okay, so today we just want to talk about properties of limits, how we can we kind of break limits down. Maybe you have a real complicated one and you break it down into simpler things of that sort. And we'll look at some examples here in a little bit. But a lot of them, they really just seem to work exactly like you'd hope they work. Right? So it says, for number one, we have the limit as x approaches c of f of x plus g of x. So we have the combination of the addition of those two functions inside the limit. We could break it up to say the limit as x approaches c of f of x plus the limit as x approaches c of g of x. And that could save us a lot of time and a nice shortcut sometimes. The second one here, we have the limit as x approaches c of f of x minus g of x. Again, you could just do the limits independently and just subtract them. So really, can be handy, and you could get a lot more in depth with this when maybe you're doing different definitions and things, or there'll be times later when we're working with derivatives and I'll be like, oh, remember this limit rule, and we'll split one apart and something neat will happen. 3, the limit as x approaches c of f of x times g of x. Again, you can take the individual limits, multiply them together. Here in number 4, we have the limit as x approaches c of k times f of x. K just being a constant, right? So if it's, you have 3 times the function, you could just pull the 3 outside and do 3 times the limit of the function itself, right? So if there's a constant multiple inside, you can bring it outside to do that. Rule number 5 is the limit as x approaches c of f of x divided by g of x. Again, you can just take the limits, the individual limits, and divide them, with the caveat that the limit as x approaches c of g of x can't be 0, because we still can't divide by 0, right? That's not a thing that we do. Here, these weren't listed, but these are something we'll use. This one's really, it comes up enough that you want to be sure you're aware of it. But if you have the limit as x approaches c of some constant, right? Now, if you think about that graphically, a constant, if you have a graph of, the function would be y equals k. It's just a horizontal line. So the limit everywhere on this line would just be k. Like, they all have the same value. So that's one. It confuses people sometimes when they see it. If you have, the limit as x approaches 6 of 5, well, as you approach 6, the output's just going to be 5. That's what you get. Now this last one here, we actually need it for one of our examples. It's a little bit more, I don't anticipate us having to use this one on an assessment or anything, but it does pop up on this worksheet. And I think it's a really kind of interesting thing to look at. So I just wanted to kind of give you an idea of how this limit wasn't in our textbook. We used it on a worksheet. I wanted to actually verify it was true, though, because I wasn't sure. So we're just going to draw a little picture to kind of reason it out here. But it says the limit as x approaches c of f of negative x is equal to the limit as x approaches negative c of f of x. Okay. And hopefully you can kind of see it works, because if you plug c in here for x, you get f of negative c. Right? If you plug negative c in here for x, you get f of negative c. So you should have, if you look at the substitution value, it should work both ways. I just thought it might be nice to kind of talk our way through this. And just if you do get stuck sometimes with properties, this is kind of how you can work them out. So I'm going to go ahead and draw the generic calculus curve, which we'll call it y equals f of x, I guess. It's fine. It needs a name, right? So let's take some value c over here, some on the x-axis. We have some value c. Okay. Now, if we have this curve, we know that there's going to be a limit there. So I don't know if there's actually a point there, but I can at least know there's a limit. So I'm going to leave an open circle. And let's just say that that value is, we call it a. I mean, we use c, so a seems like it should be used, right? And then over here, we have negative c, right? So if this is 5, that's negative 5. Right? And again, it's just kind of an idea of how we can talk about things or how you might prove a theorem or things like that. So here, if I look, there is a limit there. We're going to say there's a limit, or else this all doesn't make any sense. We'll call that limit b. So what we have here is we have that, pull this up a little bit, we have that the limit as x approaches c of f of x equals a, right? And then we have that the limit of f of x as x approaches negative c is b. But we really want, well, these aren't the same actually. So what we're going to do here to show this is we have this here, but what we want to look at, I guess, is, we know that one, but what I want to look at now is if I do this limit as x approaches c of f of negative x, what would that give us? Right? So here, when I do this, because that's what our property used, the limit as x approaches c of f of negative x, right? We're taking the x value and making it negative. So when I try direct substitution here, I'm going to get f of negative c, correct? Well, f of negative c is b. Right? So these both equal b. Therefore, they must equal each other. I think I wrote it backwards from how I had it before, but it will give us this property, which is the one we're going to use here in a minute. Basically says if you have a negative x in here, right, you could take the negative out and put it down here with the limit you're approaching. It's going to be helpful for us. Okay? Or vice versa. If you have a negative down here, if you need the negative up there. Does that make sense, though, how we can kind of reason that out using a picture? Right, we had our two things. We showed they were equal to the same thing. Therefore, they must be equal to each other. Okay, so for our first example here, we're given all four of these facts here. The limit of f of x as x approaches 2 is 4. Limit of f of x as x approaches negative 2 is negative 3. G of x as you approach 2 is 1. And the limit g of x as we approach negative 2 is 6. We're asked to find the limit of f of x plus g of negative x divided by 2 as x approaches 2. So what we're going to have to do is use the properties we just looked at to break it apart. So we see a big addition sign right in the middle. Right? That would probably be a great place to start. So let's say that would be the limit as x approaches 2 of f of x plus the limit of g of negative x over 2 as x approaches 2. So in terms of breaking this down, this is kind of done, right? We know we're just going to replace that with a 4. This one, got a little bit going on here. I guess you could think of this as a limit divided by a limit, but really, if you see a 2 on bottom like that, that just means you multiplied by half. That's by far the easiest way to do it rather than do a limit over the limit of a constant. Because you can always move constants out, you really should not be taking the limit of a constant unless you just want to, just extra work. So here we'll get limit x approaches 2 of f of x plus 1/2 limit x approaches 2 of g of negative x. Now this is the case where, because we have a negative x in here, we can make this a positive x, and we can make this x down here a negative 2. It's like we're just moving that negative on the x from one place to another. So that's the limit as x approaches 2 of f of x plus 1/2 limit x approaches negative 2 of g of x. Right, so we, again, to deal with that negative, we went ahead and moved it down to where we were taking the limit. That was that diagram we just had up here, which moderately successful explanation of it, I think. So with this, can we plug in for all this stuff? We said that was 4. 1/2 is, still 1/2. And then the limit as x approaches negative 2 of g of x is 6. So I think we can. So we're going to get 4 plus 1/2 times 6, and that gives us 7. And one way to know that's correct is the answer is written at the bottom of the page, and it says 7, so it makes us feel good. Okay, for our second example, we have the graph here from our worksheet, and we see that, you know, it's continuous from like negative infinity up until 0. Then we have a removable discontinuity, and then it's continuous until 3. There's a jump discontinuity and some things like that. So for this, the first one says, what's the limit as x approaches negative 3 of f of x? The thing to remember here is we are looking at a limit. So we're going to do the composition the same way we've always done it. But when you go to find the limit of f at negative 3, you would actually choose the limit versus the value if there's a difference. So on this one, if we look at, so you're basically doing the limit, well, I guess kind of think of this as the limit of f of negative 3, right? We're doing substitution here. So with this, or actually, well, it's just still a limit. I guess I could still say as x approaches negative 3. I'm not sure about notation exactly on this one. We just want to get the answer. But at negative 3, it looks like our output's about, what is that?
1.
About 1, yeah, just shy of 1. So then when we do the second f, would be at 1, and the output would be 0. There were no limits there, so we didn't have to make any tough decisions. Okay, let's look at the second one, just kind of to be sure here. We have the limit as f of x of 0, so I'm not sure that was a great thing to write, but we're going to put 0 into that limit. So what is the limit at 0? Is it 1 or is it 2? It's 1 because of the discontinuity. And then I take 1 and I plug it in and I get 0. Does that work? Pretty straightforward? Okay. So, yeah, I guess that's kind of it. That was. Okay, so for 3a, we're given all this information here, right? These are actual values of functions. These are actually limits. So, is it continuous at 3? Is f of x continuous at 3? No, the limit's different than the value. Right? None of them are continuous at 3. Just kind of interesting to look at. But we have to find the limit as x approaches 3 of h of x over f of x plus 2g of x. We're going to have to use our properties to kind of break this down. Now, this is just h of 3 out here. So that's going to be negative 6. Like we know that already. It's just one of the values, one of our givens. So for this, let's split it into a numerator and denominator. So we have the limit as x approaches 3 of h of x. And then we have the limit as x approaches 3 of f of x plus 2g of x plus h of 3. Now, could I have broken that more? I could have done more. We still should, right? It's still got a plus in it, so we can do that. So then we could say the limit as x approaches 3 of h of x, and then the limit as x approaches 3 of f of x. I want to pull the 2 out of here, right? So I'm going to say plus 2 limit g of x as x approaches 3 plus h of 3. So again, I'm just using my properties. We had a sum of 2 functions. We can take the limit of each one independently, and then you get a constant multiple of 2, so you can pop that 2 outside. So now at this point, I should be able to substitute for everything, right? This is going to be 3 is the limit of h of x as x approaches 3. And then the limit of f of x as x approaches 3 is 1. And then 2 times this limit of g of x as x approaches 3 is 2. And then we're told that h of 3, we've known the whole time, is negative 6. So at this point, we get 3/5 minus 6. So let's see, 3/5 minus 30/5 is negative 27/5. Or you could have said negative 5 2/5 if you wanted to, whatever you want to do that. Okay, so again, it's just kind of breaking that down into pieces that we identify that we know, and then we can evaluate those. Okay, our last example here is just kind of going back to this is just find some limits based on a piecewise function problems, but since they had trig functions, I thought maybe we could look at them because these seem to confuse people sometimes. So a lot of this stuff looks strange. H of theta looks weird. It doesn't mean, theta is just a dummy variable. It just shows you where the input's at. Right? Tend to use it with trig functions. So the first limit is of h of theta is x approaches pi from the right. Okay, so we want to find, we see there's two of these that have pi involved in them, but the right would be where it's bigger than pi, where theta is larger than pi. So that tells us for A, for this first limit, we're going to do this rule, the sine of theta over 2. We'll try direct substitution. So theta is pi over 2, and as everyone knows, the sine of pi over 2 is 1. The answer is 1. Okay. Here for B is we have the limit of h of theta as theta approaches pi over 2 from the left. On the worksheet, this is an x, and it should be a theta. This is what I overlooked that. So with this one, if we look at pi over 2, we see that the kind of the border, or like where pi over 2 changes functions, is one of those points, right? And with that, we will just want to do the left-hand limit, so we want to look at where theta is less than pi over 2. So that's going to give us, with direct substitution, the cosine of 2 times pi over 2, which is the cosine of pi, which we all know is, it's -1. Right? So it's like 0 minus 1. I thought it was 0. Do be careful. I guess something that doesn't come up a lot, and we really probably have not mentioned it. Say that you have this problem and you're asked to find the limit of h of theta. This is not C on your worksheet. This is just a bonus fun problem. As theta approaches pi over 4 from the left. This could have a tendency to confuse some people. But with this, is pi over 4 any of our dividing lines? No, but which interval would it fall into? Be the first one, correct? Now, because it falls right in it, you actually can find the two-sided limit, right, at pi over 4. I asked for the left-hand limit just to see if we could calculate it, right? But you would still use the same property. And you would just say that this would be the cosine of 2 times pi over 4, which is the cosine of pi over 2, which is 0. Is that good? So sometimes if it's not, you can answer all the limit questions from a piecewise function. And again, also here, this would have been the same as if I had just done the two-sided limit or the right-hand limit at pi over 4, because they're both defined by the same rule. Just want to make sure you're aware of that. And just to wrap up today, this is from a prior worksheet. We just want to evaluate this limit algebraically. So we know the first thing we're going to do is try direct substitution. All right, so when we try direct substitution, you get 1 minus 5 on top, which is -4, and on bottom you get 0. Now, we know that you can just put does not exist at this point, right? So if you put does not exist, it's fine. But we can actually investigate what's happening here, right? And also when you get this case, it's going to be an infinite discontinuity. But we can investigate what the left and right-hand limits are doing so that we can make a decent graph for this. And we can do this pretty easily. We don't need a calculator. We don't even need to calculate much. So what we'll do to find the left and the right, so this one, again, one answer is we could just say does not exist. You'd be good. But let's look at the left-hand limit just to kind of dig a little deeper here. So we have x squared minus 5x over x minus 1. So we're going to go, we want to pick a number, we're going to approach it from the left, so just think about numbers a little bit less than 1. Okay, a little bit less than 1. So as we do this, if you put in a number a little bit less than 1, I mean I could even make a table if you want, but say I put in 0.9 or 0.99, really close to 1, but to the left. I'm not going to do the math with that, that's crazy, right? That's too much work. But I know the numerator is going to be about -4, right? It's really close to -4. put 1 in there, you get negative 4. So 0.99, you get really close. Now the bottom is going to be 0.99 minus 1, which is a really small number, correct? And if I get closer, it's going to get even smaller, and even smaller, and even smaller. But it's going to be a small negative number. And we know that if you take a constant and divide by an increasingly smaller number, you approach infinity, correct? Well, here we have a negative divided by a negative, so we're going to approach positive infinity for this one. Right, so that tells us that on our graph of whatever is going on here, which it could be lots of different things, but as we approach 1 from the left, it's going to go up like that. That's all we know. Like, could do lots of other things. Does that make sense, though? Why it would be positive infinity? And then for the right-hand limit, okay, well, with that, I would pick a number like 1.01. And again, I'm not plugging it in. I'm just using it to help me think about it and make sure I'm going to get the right positives and negatives. That's pretty much all I'm doing. So the top is going to be about negative 4. The bottom is going to be a small positive number. Right? And as we get closer and closer to 1 from the right, the bottom is going to get smaller and smaller. So we know that we're either going to approach infinity or negative infinity. But here we have a negative divided by a positive, so this would be negative infinity. So that means in terms of your graph, as you approach here at 1, it's going to be going down towards negative infinity as you approach 1 from the right. Yes?
So if the power is bigger on the top, does that mean it's always going to approach infinity?
Okay, great question. The question was, if the power is bigger on top, we know it's always going to approach infinity. I think you're thinking about end behavior models.
Oh, yeah.
So that would be where our limit goes to infinity. So, but the answer is yes. If, for this function, if we did the limit as x approaches infinity of x squared minus 5x over x minus 1, right? We know that our end behavior model would just be x. When you put infinity in there, you get infinity. So as it goes to the right, it goes up. This is equivalent to saying, f of x approaches infinity as x approaches infinity, back in pre-calc. Okay. But yeah, be careful. That model is just for when you go to infinity or negative infinity. It won't work anywhere else.